You guys are good to go whenever you're ready.
Okay, well, we will start off. I am McKayla Plett, and I am a high school teacher and administrator at Seminole Public Schools.
My name is Mandy Ramirez, and I am with Union Public Schools, but I teach 7th grade science.
And to start off with, Mandy and I spent our summer in the FEARS lab, and I've been told to make sure that I emphasize the historic FEARS lab here on the South Campus at OU. And this is one of the pictures that we took on our very first day in the lab from the very end. And this is civil engineering. It's their home. It's where they go and they do their projects. And it's a very hands-on mechanical lab. And Mandy and I really, really loved our time there. It was an exciting, cool lab to get to be in all summer. Not cool temperature-wise, but cool, interesting.
The hottest summer in 10 years.
Yes.
No air conditioning.
None at all.
Alright, so a little bit of an overview of our research. So we were in the lab with Dr. Shreya Vemuganti, Haiba, who was our graduate student, very patient person, took all of our many questions from us, and then Miss Stephanie, who's an undergrad, who actually came in about, middle of the second week. We actually knew more than she did at that point, so we got to see her actually learning from the collegiate level as what a college student would see when they were coming in. So it's been very awesome. So what we did is we actually were testing and researching with different materials. We looked at carbon fiber, then we were looking at glass fiber, and we saw the unidirectional glass fiber, which is actually this right here, and then the bidirectional glass fiber. And we did what we call these layups, where we had to layer a lot of different materials. We call them FRPs, or fiber reinforced polymers. With these layups, we actually had different methods, and we even used epoxy resin to strengthen these materials and kind of bond everything together. And then once we had these materials, we cut them out into large plates. Sometimes we vacuum layup, sometimes we didn't. And then sometimes they would be put in an oven, or sometimes they would be put in basically a freezer and frozen for several days. Okay, so the big idea is to use these FRPs, or fiber reinforced polymers. These materials can reduce the weight and increase load or durability and ductility of materials it is added to, like concrete. As you can see here, we've got some samples. This is one of our testing here. This is one of the concrete samples that we looked at, and then these were our testing that we actually did, which is actually made from the same plate that we used to make these turbine blades here in our little model.
So throughout the summer we did, like I said, the lab is very hands-on. We did a ton of different stuff. And so the best way to show that to you is we made a very short video. It's about 2 minutes, and it's just snapshots of what we did. And so we're going to show you the video, let you just see some of the different things we did, some of the different processes. There's no way to do one slideshow that shows you everything that we did. So we're going to show you a video of that, and then the rest of our presentation we're going to talk about what we were doing in the video and how that related to the research that we were doing.
May you have auspiciousness and causes of success. May you have the confidence to always do your best. May you take no effort in your being generous, sharing what you can, nothing more, nothing less. May you know the meaning of the word happiness. May you always lead from the beating in your chest. May you be treated like an esteemed guest. May you get to rest, may you catch your breath. Or may the best of your todays be the worst of your tomorrows. Whoa. Or may the road less paved be the road that you follow.
Oh, sorry.
Oh, oh. Well, here's to the hearts that you're gonna break. Here's to the lives that you're gonna change. Here's to the infinite possible ways to love you. I want you to have it. Here's to the good times we're gonna have. You don't need money, you got a free pass. Here's to the fact that I'd be sad without you. I want you to have it all. I want you to have it all. I want you to have it all. I want you success. Having no possessions, though immeasurable wealth. May you get a gold star on your next test. May your educated guesses always be correct. And may you win prizes shining like diamonds. May you really own it each moment to the next. Or may the best of your todays be the worst of your tomorrows. Whoa. Or may the road less paved be the road that you follow. Whoa. Well, here's to the hearts that you're gonna break. Here's to the lives that you're gonna change. Here's to the infinite possible ways to love you. I want you to have it. Here's to the good times we're gonna have. You don't need money, you got a free pass. Here's to the fact that I'll be sad without you. I want you to have it all. I want you to have it.
Okay, so that is
Very
just,
good.
thanks. That's just a brief, like I said, snapshot of the different things that we did. Probably the most interesting thing in the video is if you saw Mandy and I up on the ladder with the little mallet. So where Blair was talking about how their machines are so like sensitive and things like that, a little bit different in the Fears lab. We actually had to attach that when Hyba did this portion. You hook that to a crane. You have to lift it up, and then you take out these giant bolts, and then you have to lower it, and then you put the giant bolts back in, and this is heavy machinery. We had to wear steel toes every day. So it's a little bit different. It's not the like, but then you put that little tiny tester on it that does measure those tiny little things. So it was a little bit different of an experience for us. So where we go with this?
So how does this, the big question is, how does this really tie into renewable energy? Well, when we're talking about renewable energy, one of those big things is wind and using those giant turbines. So then going into a little bit of background information on how these structures are actually made. If you guys don't know this, but the massive, really huge wind turbine blades, the very tip of them can reach about 180 miles per hour. That's about the same speed as a Boeing 747 at takeoff. These blades are subjected to an immense aerodynamic, inertial, and even gyroscopic loads. They must be made out of lightweight material that can withstand it, but also be flexible at the same time. What we found out is using a glass reinforced polymer, that substance exhibits all of those different properties. Which is what they use to actually construct all of these blades. And they use like an incredible method to do that, and it actually only takes about 2 days from start of a blade to actually when it's being wheeled out ready to be shipped. It only takes 2 days. It takes about 100 people and lots of different testing. When they use the glass reinforced polymer, sometimes more towards the tip, it's kind of used almost like solo or monolithically, and then towards like the base and the wider parts, it's constructed with balsa wood in a sandwich construction with a thermoset, about 75% glass fiber, and they're wanting to try and use an alternative to replace or complement the glass fibers, including carbon, aramid, and basalt, which actually gives stiffer, lighter, but it's also at the same time more expensive. So we're trying to make them lighter, stronger, more durable, and at the same time still be incredibly flexible at the same time.
So when we look at these images that are on this page, this top one right here, this is the material that's used to create these layups. This is almost, it was funny, we were looking at this presentation yesterday with Stephanie, and she was like, oh, that looks familiar. This is almost identical to the material we used in our lab to create our layups. The same material that we used to create this layup right here. That's this glass fiber right there. That is, it looks just like this. That is the material they use, they put inside the wind turbine blades. So when they do that, it's just unreal to me, because this is a wind turbine blade. You can see the size comparison, the guy standing down inside the blade to construct that. They also use a vacuum, okay? So they have just tubes all along here, and they do the vacuum layup, and they're sucking out the extra resin. They're making sure that the resin permeates all of the material equally so that there's no weak spots or spots with too much resin throughout the blade. And that's what we were doing this summer. That's what we were experiencing, just on a much smaller scale than this. So after they do that and they've made the two sides to the wind turbine blade, they put them together. And they glue them together with more epoxy resin in the middle. And these are made to withstand and last for about 25 to 30 years. So what does that mean as far as renewable energy? We've talked about this, we went on field trips, we learned that that's a big issue in renewable energy right now. Where do these go when they're at their end of life? And through our research, which unfortunately is not the research we did this summer, but through our research, we learned that there is research being done to try and figure out better ways to dispose of, recycle, or make these wind turbine blades to have better function at the end of their life. Whether they can be recycled different, they're trying to use, some companies are trying to use different resins to begin with that make them easier to recycle, but with that's a trade-off. They're not as strong. So that's a concern. And then another thing that they've looked at doing is at the end of life, which Hyman and I talked about this yesterday, and he was like, ooh, and it's what he was thinking before I even got there, is they are talking about grinding them up, using small chunks, putting them into concrete. And that's one of the big things they do at Fears Lab, is they make concrete, try to make concrete stronger. So that would be a potential research thing that they could maybe do at Fears Lab. But it's a very fascinating thing. And this is, as far as renewable energy goes with wind turbine blades, one of the biggest things that's being done right now is what do we do with them at the end of life? Because we're kind of getting to that point with several of those. So now, what did we do with our wind turbine materials and blades?
Okay, so what we looked at with, especially with the glass fiber, is we were testing tensile strength, or how much can this material withstand, what kind of load can it withstand before it completely fails. And what we looked at is, can this material withstand the wind load if it's used in a wind turbine blade? So we looked actually at the different, we actually looked at carbon fiber first, and then we were looking at glass fiber. So we tested the different fiber materials. We used like actual different fiber angles. So if you don't know anything about carbon fiber, it is very intersectional, so just straight up and down constantly. But they also have a 3D printing machine where they're actually able to print using carbon fiber, and then instead of just doing it 90 degrees, they'll change the angles. So we looked at like 12 degrees, 20 degrees, 45 degree angles to see if that would affect the strength. And we also used a couple of different companies in epoxy resins. One of them was really, really, really smelly, and we had to use us with the gas masks. That stuff is really, really strong. And when you're in a lab like that had, you know, hottest summer in 10 years, yeah, it was sweat would be pouring down. And then we also tested different layup methods. Like earlier I said that we used the vacuum layup compared to others where we didn't use the vacuum layup. So we got to test all these different. There's actually an image of one of our tests that, again, those are the same material blade that we had turned into that. So now, why do we do this? So why do we want to find the tensile strength? Because we really want to figure out how strong it is, and again, how much load it can take, and if it can even add strength to other materials. Like we keep talking about concrete, and one of the ideas is to, when we're talking about concrete for buildings, roads, and bridges, right now what they use is those steel rebars. And the idea is to, those steel rebars, they hold it together, but at the same time, once the concrete has become weakened, like say an earthquake, that concrete will then break off and then chunks, and then the buildings and bridges will then collapse, and then people will be trapped. So the idea is to add these FRPs, or fiber reinforced polymers, to strengthen this and actually hold it together longer. So instead of structures completely collapsing, they might break a little, but they're not going to completely collapse, giving more people time to get out, bridges to hold stronger and longer. And then, so that same application that can be making things stronger, at the same time it can also be very flexible, and that we use for wind turbine blades. And then that application can then be turned around into aviation and be used to construct airplanes.
And lighter airplanes means less emissions.
Yes.
Learned about the other day.
All right, so the research that we did, and we're getting ready to get into the data that we collected and the testing that we did. These test results are shown in graphs. That again, we use the glass fiber. We use the glass fiber with the U.S. composite epoxy resin. So we kind of chose the materials and the resin that we were going to use for this testing, and then McKayla's going to actually walk us through the graphs.
I'm going to go ahead and while we're talking about this next section, I'm going to pass these out to you. This is actual samples of what we test, what we put in the machine. Do not touch the middle part. It is glass fiber. So touch the end portion. The end, as Mandy said, the middle is glass fiber reinforced polymer. The end is carbon fibers. These are fine to touch. So we make the tabs out of carbon fiber. We learned from Hyba that the carbon fiber is stronger. You want to put those on the ends because that's where you actually attach it into the machine, into the MTS. You put the most force, tighten the thing onto there, and that's going to allow you to have the most accurate testing when you're completing that. So this is before testing. This is what it looks like. We didn't actually run this one through the test. And then after testing, this is what you want. This is what you want it to look like. If it doesn't look like this at the end, Dr. Vimagati comes up to you, she pulls on it, and she says that test did not work. And so then you don't use that data and you go and you do another one. You want brooming. You want it to look like the kind of end of a broom. So that's the goal.
That's what we would call a complete failure. We don't just want pieces. We want a complete failure.
So the first thing we had was, oh, I didn't change that twice. Our hypothesis, you can't see it, I know what it says though. It says that our unidirectional glass fiber is going to have enough ductility, it's going to have enough strength to withstand wind load, and it's going to function as a residential wind turbine blade. I want you to understand when we say a residential wind turbine blade, we're not talking about the big industrial ones that the companies put up. We're talking about if you wanted a wind turbine blade to put in your backyard and to power your house. And I'm not talking about like a little one like this size that you just put on your roof. I mean like a big one that would power your house. So like a 30-foot to 35-foot long blade. Yes?
Would it be similar to ones in Atlas?
Smaller.
Smaller than that one?
A little bit smaller than that one. So like when we drive along the interstate and you see the ones with the little yellow, about that size. Those are more accurate. Okay, so now we're gonna look at, push the wrong button. We're gonna start looking at our actual testing we did. So these are two of the graphs from some of the testing that we did. And this shows the linear elastic response. Hey, Dr. Okay, so this is an example of, this was test one. And you can see as we added load to our specimen as it was in the machine, it went up, showed a linear elastic response, and then at the end we had brittle failure. It snapped, it started that brooming, and every single one of those tensils, you can see a jump in our machine as they snapped and it went down and then had the complete failure at the very end. So that, all of our graphs, we have about 7 of these. We put them on the same graph. You can see the same trend in all of them. They're not identical, but very similar. Linear elastic response and then brittle failure at the end. These were displacement control tests. Dr. Vimagati made sure I got that correct. And so that is what it looks like. This will show us how much load each specimen was able to take and then how much displacement we put in to have that load. So that's what our test showed us. Now we're going to show you what that meant towards our hypothesis as we went through our data. So this is where we didn't get to play with the machines anymore and we had to get paper and pencil and do some math, which is not really the fun part unless you like math, which I kind of do, so it was kind of fun. But we, first of all, full disclosure, we did not do the super high level wind load calculations and all of the extra calculations that people who actually do this as a career do, okay? Just gonna disclose that right now. We use the generic formula for wind load calculation, okay? And the generic formula is area times pressure times drag coefficient. That is the formula we used to determine the wind load based on the average wind speed for a certain area, okay? So we did it for 2 wind speeds. We used the average wind speed in Ada, Oklahoma, which is where I live. Newsflash, not super windy in Ada. Hyba was shocked by this information. The average wind speed in Ada, 9 miles per hour. That's over a 100-year span, okay? honestly, not a great spot to have a wind turbine. It's not like, we're not gonna produce a lot of wind power, so solar is probably my best option if I want to use a renewable energy. So from this, we calculated what our wind load on a wind turbine blade would be. The amount of pounds per square inch that would be pushed on a wind blade of wind load would be 52.4 for Ada, okay? We were like, that's really low, that's probably not accurate. So we looked at what the highest ever recorded wind speed in the state of Oklahoma was. 151 miles per hour, that was in El Reno, definitely during a tornado. Okay, so we calculated the average wind load, okay? And then we figured out how much pounds per square inch of pressure that would be on the wind turbine blade. Again, there's lots of other calculations that should go into this. We did the generic formula. It would be about 339.5 pounds per square inch. Okay? So then from that, okay, we got that information. Now what we need to know is what pounds per square inch can our tensiles, our things that we tested in our MTS, what can they withstand? Can they withstand that amount of wind load and be able to function as a wind turbine blade? Is that possible? Is that something they can do? And so, Mandy?
So with our machine, the reason why these look like this is because there's the American Society for Testing Materials standards. So these specimens we cut about 15 millimeters wide, about 56 millimeters long, and about 1 millimeter wide. So when we measured off here because we had to measure the area. So when we put it in our MTS machine, we have this right here, and I'm so sorry, I always forget what this extensometer.
Extensometer.
Yeah, the extensometer sensor is about 1 inch wide, which is about where these are, and then we put this on here so that when we're in the machine, it's at a rate of, literally pulling at a rate of about 1 millimeter per minute, and then this is testing the displacement, and then once it gets to its point to start breaking, it starts cracking, and it makes this coolest sound, and this is what it ends up happening. So what we found out from this testing is that the average stress for this unidirectional glass fiber plate was actually 57,797.5 pounds per square inch. So what we found out is that not only could it also withstand the highest wind rate or wind speed in Oklahoma, but it is actually way higher than that. So we determined that yes, it definitely does have that strength.
Okay. So that being said, on to our conclusion. That's what she just said. From the testing we completed, the glass fiber is lightweight, it's got high strength, it's durable, making it excellent material for wind turbines. That's probably why that's what everybody uses. It has average stress required is 52.4, ultimate stress 339.5. So in the testing we completed, it withstood that 57,797. So therefore the material has more than enough required strength to withstand the stress. And again, this is the most common fiber used to construct the large wind turbine blades. So I mean, we weren't really shocked by this revelation. I was shocked by by like how much higher it was. That was kind of shocking, but again, there's a lot more calculations that go into that. So we just did very generic basic math to determine what the wind load would be, but it was kind of a shock to see how large of a difference it would be. So we brought our model that we made, and we made the tensiles that we tested came from this same plate. Okay, so these are from those tensiles. All of those numbers that we ran came from that. Now, it just sitting on the table, y'all are like, we don't even know if that works. So we videoed it so we can show you that it works.
3 different videos actually.
When you put it in front of a fan, it absolutely works. So we want to show you that. We have a couple videos of that. This, again, Mandy yesterday, I added this little part because her and I were sitting down doing our presentation, and she said, everybody's gonna look at us and be like, what does that have to do with what we did? Nothing really. But we took our layup, and we made something out of it, and we used the GFRP, and it's what we use to test. So we just wanted to show you what we did and what our lovely people at the lab helped us complete and helped us brainstorm to get there. So it's something we're kind of proud of, and it's cool to be able to take back to our kids and show them. So we started it from just stationary, turned the fan on, and it goes pretty good. So
How big was the fan you were using?
I don't know.
Probably about as tall as this table and
It's
about
like a
box fan.
fan. Yeah, it's a box. I mean,
2
yeah.
feet wide.
And then because no good video is good without doing I don't know which is which. This is slow-mo. You have to have slow-mos. So this is a slow-mo video of it going, because it just looks cool.
And I wanted to calculate the wind, like at what speed it was spinning, but we weren't able to.
Listen, I love engineers, and I love I'm a teacher for a reason. I love it. I have a passion for it. But we were talking about our presentation in the student room at Fears Lab yesterday, and we were talking about our video. And like 2 of the other students, there's students all over Fears Lab doing work. And he came in and he was like, oh, you could calculate the something, something, something. And I was like, go back into the lab. We are not doing that. Like, I love that, but no, that is unnecessary. Like, and then this is a hyperlapse video where it just looks like it's going super fast. So, yeah, great time. We learned so much in this. It's something I'm definitely going to take back to my classroom. My students, I teach aviation as well, and like she mentioned in the process about airplanes absolutely use composite fibers, carbon fibers to produce, and being able to show them this and show them how that process works and not just like say it, I think it's something that's going to be really beneficial. We did, like I said, do some research outside of the hands-on research, and this is our references for that. Pushing the wrong 10. And then we got to go to all these awesome places, had outstanding speakers throughout our experience while we were here. And this is just some of the logos. Mandy had written down all of the people, and so she was like telling me them while I was searching for their logos.
The only ones that we didn't get were the ones that were the most recent.
Yeah, so we had all the others. So huge thank you to all those people for taking their time to come speak with us. And then absolute thank you to Dr. Vimagati. Thank you so much for coming into the lobby and just like giving us your wisdom the other day when we were working on our presentation. And Haiba, he dealt with us all summer long, bless him. Bless him. We asked him silly questions. We learned so much about Somaliland and his home, and that was such a cool experience as well. And then Stephanie, she came in about a week and a half after we'd been there, and it was really neat to get to learn about her and her college experience here so far. And John, he's the lab manager at Fears, and he was super helpful with teaching us equipment and all of the things like that. Dr. Nanny, thank you for allowing us to get to come here and do this experience. And Dr. Tessman for ECU, and Claire, you're the best. I know I've given you a terrible time while you've been here, but thank you. Thank you so much for all of your help. And Mandy, I've enjoyed working with you on our research. It's been great to have you to bounce back and forth. So we appreciate it. Does anybody have any? Yes, Aaron's dying to ask a question. What is your question, Aaron?
It's a serious question.
Okay.
Okay, so you can't touch that carbon fiber.
Right.
So
This isn't fiberglass. Glass fiber.
sorry. Yeah. So what is different about the actual wind turbine? What's on the outside of the wind turbine?
It's still, they coat it.
Yes.
So they put a special coating
So
on
there's
it.
a coating you can put on that, but it would be.
Yes. So
Okay.
Mandy and Haiba both suggested that we paint it.
Yes.
And I turned it down
Okay.
because it's going back to my
You
classroom.
live on the edge.
I do. Which is probably a bad decision because my children are going to try and touch it.
Students touching it. Yeah.
But I want them to see it.
Gotcha.
Like I really want them to be able to see, and it's kind of clear now. And so that's why I said I didn't want to paint
So
it.
even painting would help.
Yes,
fix that
you
problem.
could put like a coating on it and keep
Okay.
it where it wouldn't. But they do
Not
put a
have
coating
duct
on it.
tape on it.
Yeah, but even when we were at the one at High Plains, like I could see the glass
The
fibers.
one that was on the ground?
Yes,
Okay.
and I could I touched it and I was like, this would, yeah,
Okay.
yes.
So this is,
Clear.
Huh?
You could paint it.
I could, hey, David, boy, you gotta bring logic into this.
I feel like it's.
You could
paint
paint one.
I could paint one, yeah, okay, y'all.
Oh, polyurethane will work.
Yes, I could paint it clear. I could paint one of them. You're
It's
right.
yours.
You're absolutely right.
Yeah. So to kind of give you guys a better idea of what the materials were, so this is carbon fiber. If I'm brave for touching that.
Yeah, you are.
So
I'm
this
not
right
doing
here, this was a really difficult material to cut constantly because it just, I mean, I can barely pull it and it just wants to kind of pull apart. And then it reminds me of like the material in trampolines, like you would jump on and stuff like that. But then when you look at the glass fiber, you can say that this is pretty thin, very lightweight. Glass fiber, or this one specifically, this is the unidirectional. It's a really, really thick and kind of heavy, or it's heavier. And if you thought that was difficult to cut, oh my gosh. Once we did the layup and it became this really hard, like tapping on it, you guys can hear me tap, it got really, really thick. This one, if you guys can actually tell, there's a little bit of a difference in this blade. You can almost see more of the glass fibers. This one didn't end up as saturated with the epoxy resin when we were laying it up, because once we do layers, each layer you had to put like a layer of the epoxy resin, and we did that several times. And then this one we were like, no, just keep pouring, keep pouring, keep pouring. So these actually became so saturated, like we could barely bend it. But luckily, with the way that these are, it's a lot harder, obviously, to bend this way than it was to bend it this way once it was hard enough. So I actually had to take this to the bandsaw, and I had to, that's why you saw me, the black lines, because I had to cut, shape it out, and then I had to use the bandsaw to cut it out. So it got pretty tough, and then trying to get it to fold over and glue. So once you do the layup, you have to mold it to whatever you're doing too, because it's going to stiffen up.
So, so they replace these blades, so they wear out in some fashion, which, I mean, you indicated it's super strong, so what's failing? That requires replacement.
So when they reach their end of life, if they like have like a crack in them, so because this is, I mean, like if you came up here and you went, this would break. And so even though it's super strong, they can get, like the one that just in Texas got struck by lightning, that blade's gonna have to be replaced. If they have just anything that can happen to them, there's going to be weak spots over time, 25 to 30 years. Any material that's going 180 miles per hour is going to eventually have a weakness that comes up, and it could crack, it could bend, it could not it's just not going to get, like, it's not going to function the way it's supposed to, and it's going to start having more bend than it's supposed to. And when it has more bend than it's supposed to, it's time to replace them.
You also have to keep in mind also with like the weather and the climate of where these wood blades, I mean, thinking about how hot this summer has been, I mean, you're going to have some, you know, expansion and some contraction with the winter and summer. So yeah, that'll, what they call it is called a high cycle.
Yeah.
High cycle
Yeah. I don't remember.
It's something like, I mean, once they go so long, and then days that, even on the hot days when it's not even functioning, that puts pressure. And then it's even more pressure when it's hot and they're actually working. So there's a whole bunch of different factors that go into affecting the material. So, but I mean, 25 to 30 years, that's still quite a long time.
Yeah.
Well, that's the hope.
But they're trying to make them longer or more recyclable.
Yeah.
Yes, Aaron?
How did you decide on the shape for that? Or just...
The shape, okay. So we found, Mandy and I struggled with how we were going to make this. And Dr. Vimagati and Haiba, and we all had lots of videos, and we looked, and we all looked, and we looked and looked and looked. And then one evening, because there was no laundry at the duplexes, even though there is laundry now that we found, I went to Mandy's to do laundry. And I took my computer, and we were sitting there, and we were just Googling things because we were bored waiting for my laundry to finish. And I found a video. And it was a guy who made one out of cardboard. And he had folded the cardboard. And I was like, well, we could do that out of these. And so we used his design, and we took, his was a little bit smaller. And so we scaled up by 1.5. I think we multiplied everything by 1.5 to make ours that size. And to be honest, Dr. Vimagati was very skeptical whether this is gonna work. We were also, but we were like, this is science, let's test it, let's see if it works. If it doesn't, we'll go back to the drawing board and we'll try something else. It did work. This is absolutely not the way they make the large blades, because what we did is we did one sheet and folded it. And you guys saw in the picture I showed you that they do a half and a half, and then they glue them together because they have a different curve in the middle on one side than they do on the other. And we didn't do that. Ours has the same size, same shape on both sides. So that's different than the large ones are. So it's not like an exact model.
You guys have no idea the brain power and the engineering
Or
cycle
lack of
that went
brain
into this. I think we changed the initial design probably every single day.
This
that we
part
did.
here, the middle.
Yeah, and then we were getting down to those last few days and we still hadn't really constructed a whole lot. So we were like, we're just gonna go, we're gonna buy some pieces so that we can help put this thing together. And then like, even this part right here, we went to the Archie Lab 2 or 3 different times trying to just find different materials.
This is a used 3D printer spool that the
Yeah.
Archie Lab gave us that we cut apart and put in the middle of, put a bearing in the middle of.
And then once we solved one problem, it created like 3 more. And then one of the things that Hyva told us at the very beginning was nothing really ever goes according to plan. Murphy's Law. I mean, every single day, it took us, we would think, oh, it's only going to take us 30 minutes to set up that machine as you saw us on the ladder. No, it took us like, I don't know, anywhere to 3 to 4 hours to finally get it set up. And then something else would happen. And when we were actually doing our testing, we had we had 6 samples originally made. And I kind of goofed up on the 5th one on accident.
It's supposed to be 1 millimeter per 1 minute.
I accidentally set it to 1 inch, and then as soon as I started, it just went. So I was like, oh no. So literally everything we did very rarely ever went according to plan without
That's okay.
some issue coming up. But we can learn how to be on the spot problem solvers for sure.
Absolutely. Any other questions? Yes, Brian.
Are glass fibers the same as fiberglass?
Does it matter which way you say them?
Yeah, we kind of use it
No,
interchangeably.
okay.
Glass fiber reinforced polymer, so it's just GFRP. Fiberglass, it's just another way around, but both of them basically represent the same thing. You have carbon fiber, glass fiber, Kevlar, aramid, different kinds of fiber types.
Kind of use it interchangeably.
But that's a great question though. Why do you think we didn't use carbon? Or when you went for your site visits, which fiber type were they using?
Almost like the wind blade at High Plains was fiberglass because I looked like really like close at it, and I because everybody was like leaning up against it, and I was like, I'm not doing that because I could see the fiberglass on it, and I looked at it specifically to see what it was, and then when we did our research. After like the fact and we're looking up some of the wind load and what they take, it was almost unanimous. Most large wind turbine blades are made out of the glass fiber. Now residential ones, like the smaller ones this size, a lot of times they're not made out of that large, they're plastic or things like that. They don't use the things that need to take that much load. But
So why do you think it's glass instead
I
of
think,
carbon?
in my experience from what we did, this seemed to be a bit more on the flexible
Yes.
side. Whereas when we did the plates with the carbon fiber, if I were to bend this the same as this, it seemed like this
I
would
think
just
so.
break.
That's a
and
great
crack.
point, but
Yeah.
in general, glass fiber is just cheaper.
okay, there we go.
Really
Less
good.
expensive.
But that's great because carbon, high strength, high stiffness, glass, low strength, lower stiffness, but way cheaper than carbon.
Yeah, and I think that our slide that we had up there did say that the carbon and the basalt and everything is more expensive, and the glass fiber is cheaper. So there we go. Anything else?
Good job.
All right. Thank you.